Please be seated. So welcome to the first session of this afternoon. And our first speaker is Ye Wang, and she will talk about the effect of emission control measures on ozone concentration in Hangzhou during the G20 meeting in 2016. Please welcome.
Good afternoon, everyone. I'm Ye Wang, a second-year graduate student from NUS, and my advisor is Professor Hong Liao. The topic of my presentation is the effect of emission control measures on ozone concentration in Hangzhou during G20 meeting in 2016. I'm going to start with the current status of ozone pollution in China. With the effective reduction of PM2.5 in past several years, ozone concentration increased sharply in most regions of China. Under the background of increasingly serious ozone pollution, we want to know if ozone concentration could be controlled effectively in summer. G20 meeting provided us a typical opportunity to study it. So let's see the observed air pollutants in Hangzhou during G20 under emission control. G20 was held on 4th to 5th September in 2016, and the period of emission control is between two vertical black lines, and the blue dashed lines represent national standards for pollutants. It is obvious that all pollutants, except for ozone, were below national standard during G20, and the mean value of MDA8 ozone during G20 was up to 160 micrograms per cubic meter, but the trend of it was continuous downward. So the scientific questions are as follows. Firstly, did the emission control measures carried out during G20 reduce ozone concentration effectively? Secondly, is it necessary to implement these stringent control measures? Thirdly, how sensitive is ozone concentration to emission reductions in different sectors? According to the Environmental Quality Guarantee Scheme issued by government in 2016, areas in Yangtze River Delta under emission control were divided into 4 parts, and they are core area, strictly control area in Zhejiang province, and control area in Yangtze River Delta. And emission reductions by sectors during G20 is showing in this table, and emissions in different regions were calculated by MAC inventory in 2016. Nested simulation over Asia was conducted using GeoScan model version 1101 with magnitude meteorological field and MAC inventory in 2016. To quantify the necessity of these stringent control measures, 3 numerical experiments were designed, and the area included by control Zhejiang province experiment are core area, strictly control area, and control area in Zhejiang province. When control Yangtze River Delta experiment includes all areas under emission control. 4 numerical experiments were designed to quantify how sensitive is ozone concentration to emission reductions in different sectors, and all emissions in each sector were cut down. Comparison of MDA8 ozone between observation and simulation was conducted to evaluate model performance, and there are good agreements between observed and simulated values. Now we will move on to the results. Comparison of MDA8 ozone in Hangzhou among observation, base case, and control Yangtze River Delta experiment is shown here. And the control Yangtze River Delta experiment was the actual strategy applied during G20. We can find that the values of MDA8 ozone during G20 simulated by control Yangtze River Delta experiment are much lower than that in base case. And the main difference of MDA8 ozone in Hangzhou between control Yangtze River Delta at the base case is -21 micrograms per cubic meter. So the emission controls during G20 reduced ozone concentration effectively in Hangzhou. Comparing the reduction in MDA8 in Hangzhou during G20, we can find that controlling core area, Zhejiang province, or Yangtze River Delta could all decrease ozone concentration in Hangzhou effectively, but controlling Yangtze River Delta was the most effective one. And the difference of MDA8 ozone during G20 from control measures shows the same conclusion. So it is necessary to carry out the stringent control measures during G20. The ratios of VOCs to NOx in this case can explain why did ozone concentration decrease so effectively during G20. The reason is that core area and most of Zhejiang province were in transition zone. Reductions in either NOx or VOCs reduce ozone. According to the observation, more emission reductions should be made to keep ozone concentration below national standard during G20. So how sensitive is ozone concentration to emission reductions in different sectors? Mean reductions of MDA8 ozone in Hangzhou between each experiment and this case is shown here. We can find that industrial emission control is the most effective one, following by traffic emission control. So the intensity of industrial and traffic emission control should be improved to achieve the standard. And here is my brief summary. The control measures reduce ozone concentration in Hangzhou effectively during G20, and it is necessary to carry out these stringent emission control measures during G20. The control of emission from industry and transport can be effective to keep ozone below national standard. And the point we want to convey by this study is that ozone pollution is very serious in China, but it can be controlled effectively. That's all. Thank you so much.
Did you see any effect of the PM 2.5 decrease during G20 in terms of ozone effect?
No, we don't say, but according to the observation, PM 2.5 were below national standard after or before G20. So
you will see a difference.
Yes.
Do you plan to look at the formaldehyde NO2 ratio from like any of the number of instruments like OMI next? See whether you can see a change in the formaldehyde NO2 ratio from space?
No.
The VOC NOx ratios?
No, we didn't see it.
Okay.
So our next speaker is Yanxi Zhang, and he will talk about air quality and health co-benefits of shale gas development in China. Let's welcome.
Good afternoon, everyone. So today I would like to talk about the shale gas development in China, especially looking at its air quality and health benefits. So my motivation to do this study actually arises from several years ago when I looked at the mercury emissions from United States power plants. So we found that the emissions of mercury have decreased a lot in the last 10 years or so. Besides the emission controls, we found that switching from coal to natural gas actually helps a lot. Of course, other than mercury, the emissions from other pollutants such as carbon dioxide and SO2, NOx are also decreased a lot. So it's naturally kind of inspired me to think about, what's the situation about China? Because compared with the United States, China has even larger shale gas reserve. Actually, based on the data of EIA, so they show that the reserve, shale gas reserve of China actually is #1 of the world. So think about this. We think there is a huge potential that China can somehow copy the U.S. shale gas revolution, and then also can reduce the air quality and air pollution over there. So in the last several years, so the shale gas development in China has been very fast. if you look at this figure here, so the shale gas and production started from nearly zero in 2013, but increased to around 10 billion cubic meters per year now. So that's because of the faster technology development. And the government make a very ambitious goal. In 2020, it will achieve 30 billion cubic meter in 2030 to 100. So give you an idea, so in 1 year, in the current situation, the total natural gas consumption in China is around 200. So you can see in 2030, that's quite a large number. But there is still a lot of debate regarding the environmental risk associated with shale gas development. So for people not familiar with shale gas development, so they need to drill very deep down to the rock layer, and then put in a lot of high pressure fluid, and then use the fluid to crack the rocks, and then the natural gas can go back to the this drill and to the surface. From this, we can say it requires a lot of water and can cause a lot of environmental issues here. And then if you look at the distribution of shale gas in China, we see many of the north part of China actually faces very severe limitation of water resources, except the Sichuan Basin. The south part of China is a little better. So now this part is a major developing region of shale gas in China. But one bad thing is that this region are mountainous, and you need to drill very deep to reach the shale gas reserve there, and also it can cause some earthquake risk. So regarding this kind of very ongoing debating, so my objective here is that to evaluate the air quality and the health impact. So here I don't want to give the government or policymakers a very comprehensive answer for them. Should we develop shale gas, but at least give some diagnostic results. Okay, so first of all, for part of the study, we will give a the current state estimation. That's in 2017 is around 9 billion cubic meters shale gas consumption. So we say the minimum consumption are limited to the nearby regions of Sichuan Basin. That's a major production area, and that's because of the infrastructure of the shale gas. Natural gas pipes are still under developing there. Many of the natural gas are distributed by this compressor jars, and many of the shale gas is consumed in residential sectors in these regions, mainly in cooking, because in south part of China don't need much indoor heating, and only 26% is in industrial sectors. And we also use a gains model to calculate the emission reduction for shale gas replacing other fuels, and also using Geochem and mixed inventories to convert this emission to air quality impact. So this gives the impact of shale gas development on emissions. I divide into two parts. Because the production means when we harvesting the shale gas, we need to use a lot, many equipment that can directly emit a lot of NO, NOx emissions. And this consumption means the shale gas replacing other dirtier fuels. So which is generally the emissions from production much smaller than the benefits from fuel replacement. So this is what is the influence in the air quality. We only look at the PM2.5. We see the around several microgram per cubic meter per year in this region. And we also look at what's the impact of the production. Overall, they are in exactly the same color scale. So we say compared with the benefits, the cost is quite low. We look at the health impact. We say that around 14,000 people are saved from this shale gas replaced other fuels, and only around 300 people are excess deaths caused by this development. So that's a current state. So I also give an outlook to 2030. So at that time is 100 billion cubic meters harvest per year, and the distribution we now assume not only associated with the production rate, because the China government has put a lot of plan and resources into the infrastructure building. So in the future, we see many the gas pipeline from Sichuan to other part of China. So because of this, we assume in 2030 that the shale gas consumption should be more uniformly distributed in the entire country. Okay, so this is the result. So so of course, again, we compare production and consumption. So we say the production emissions still kind of low, but depending on how you assume the consumption happens in different sectors. For example, if you replacing coal in residential sector, so the emission reduction is quite large. But if you deploy your shale gas in power sector or industrial sector, the emission much slower. So similar results can be achieved from for air quality. So we see if you're assuming the consumption in different sectors, the same with 2017. So the contribution decrease is kind of large, even larger than if only residential coal. But if you industrial and power, we see the benefit is quite low. Very interesting if you compare with production. So sometimes we see even kind of the benefit is more than cost. So also the similar results for the kind of gases. So here so just summarize. I have two kind of policy implications. So one is that we probably need to consider how to deploy the shale gas to give the largest air quality benefit. We probably need to replace the energy consumption in residential sector. And the second is that we need to curb the emissions from shale gas production. Otherwise, because in some of the scenarios we see sometimes the cost even larger than benefit. With that, I would stop here and take any questions. Thanks.
What kind of infrastructure changes would have to be made to replace the residential coal source?
So at the current stage, most of the shale gas is in residential sector. So you just need maybe a different stove to changing from burning coal to natural gas. But for the industrial sector, I probably build totally different instrument equipment over there. That probably largely much harder.
I thought that
Boilers.
residential coal in Beijing and some of the big cities was more centrally located.
Pardon me?
What? For heating purposes.
Yeah, they already done that. But I think that from current now, most of the shale gas is still in southern part. People are not using that for space heating yet.
Okay.
I'm not sure if I answer your question.
You can talk.
Yeah, okay.
How do you determine the emission factor for PM2.5 from shale gas production?
Oh, yeah. So basically, I assume natural gas burning emits no SO2 or NOx emissions. But when you replace other fuels like coal and biofuel, I use the emission factor from GAMES model. So we're assuming that the switching fuels, but providing the same heat. The emission factor from GAMES model. Yeah. No. So we still focus on the air quality, this part. I think the thing we will say, right? Part of, yeah, I think I included that, but not a very big source. NOx is still the dominant source from production.
I will ask one question. So when you do this calculation, did you consider the cost as well as the pollution impact of, say, the pipelines? When you develop the shale gas.
You mean maybe a more life cycle assessment like that?
Yeah.
No, I didn't. So now we're still calculating the emissions from mainly the equipment kind of fueled by diesel fuel. That emits a lot of NOx, but I didn't consider the pipeline development. Okay.
Thank you. So our next speaker is Chelsea Belstack, and she'll talk about air quality. Change the title, and so
So I'm going to talk about the climate and health effects of the residential coal ban currently being implemented in China. So as many of you, I'm sure, are familiar with, the Beijing, Tianjin, Hebei region of China has some of the worst air quality in the world. And one of the reasons for this is during the winter heating months, many residents in the area use coal for heating their homes. To combat poor air quality during the winter, a coal ban is currently being implemented around Beijing, which I'm going to show throughout the presentation with the star, as well as potentially in Tianjin and the Hebei province. And this is basically a ban on the purchase of coal, and there's also an associated heat pump subsidy using technology shown here. And this is being implemented sort of at a village level with beginning in 2016 with villages sort of being added every winter. And so there's some societal and political impacts of this coal ban, especially due to the rate of the coal ban being implemented. But my work is focusing on looking at the climate and health impacts. So we use geochem to look, and first I'm going to talk about the health impacts. And so we used geochem to run 3 simulations that lasted about 12 months, and we used a custom nest for Eastern China. And the first simulation we did was looking at continued residential coal use, and then we did 2 ban scenarios. One where coal was being banned in just the province of Beijing, and we did that by zeroing out the residential emissions from the mixed inventory in that model. And then we looked at a coal ban scenario across Beijing, Tianjin, and Hebei. So here I'm showing PM surface estimates comparing the model to a single surface monitor. And we see generally pretty good agreement between the model and monitors. And this is one winter where before the residential coal ban was implemented. And so now I'm showing our base case scenario, so continued residential coal use. And this is annually average surface PM 2.5. And the main things you can see here are that we tend to have lower concentrations sort of northwest of Beijing over the mountainous regions. And then we get this smearing of increasing PM 2.5 levels starting in Beijing and increasing downwind due to emission sources in that area. And here I'm showing the percent change in surface PM 2.5 under our 2 ban scenarios. So on the top, we're looking at just the ban in Beijing, and on the bottom, we're looking at the ban in the 3 provinces. And the general pattern you see is that the decreases are highest in the ban region with some smearing sort of downwind. And when we use these changes in surface PM 2.5 to calculate mortalities, we expect that we would save about 2,000 premature mortalities per year in the Beijing only coal ban scenario. And we expect that we would save about 16,000 annual premature mortalities per year if coal was banned across all 3 provinces. And these numbers are substantial, but they only represent a small percentage of the total PM 2.5 related deaths estimated by the global burden of disease across China. Next, we looked at the radiative forcing calculation with a similar set of models. The main differences being that we used GeoChem TOMOS to include the aerosol microphysics, and we only simulated for 3 months due to computational limitations. And we calculated the aerosol direct radiative effect and the cloud albedo indirect effect. So here I'm showing the winter average atmospheric column mass, and here I'm combining black carbon, organic aerosol, and sulfate. And I'm showing this plot because it relates to the direct radiative effect. And essentially you can see the same pattern as we saw with surface PM 2.5. And here I'm showing the percent change in that total column mass under the 2 ban scenarios, with a maximum reduction of about 12% in the Beijing only ban scenario and about 36% in the 3 province ban scenario. Here I'm showing the winter average cloud condensation nuclei at the low cloud level, which is relevant for the aerosol indirect effect. And again, we're seeing kind of similar patterns as we saw with the mass concentrations, with the number concentrations. And here are the percent changes in cloud condensation nuclei, where we see a maximum reduction of 13% in the Beijing only simulation and a maximum reduction of about 33% when we zero out emissions in all 3 provinces. And so overall, we predict a net warming tendency due to the removal of aerosols from the coal ban scenario. And so with the direct radiative effect, we see a small net warming effect because the majority of these aerosols that are emitted are scattering. And so removing them actually has a small warming tendency. But we are still trying to constrain the mixing state of these aerosols in the region because our calculation is going to depend on that. On the bottom here, I'm showing the cloud albedo indirect effect. And we also see a slight warming tendency here because the clouds are becoming less reflective as we're removing aerosols. And in these cases, we only see a slight warming over the ocean because our model only looks at warm cloud effects, which are only seen over the ocean during this winter time period. And with that, I'll leave up my conclusions, and I'm happy to answer any questions.
What portion of the reductions that you saw reduce sulfate versus nitrate in this kind of studies that, especially winter time in Beijing, is a big overestimate versus that good at a species?
I'm not sure I have the answer to that right now, but that's a great question.
What is the implication on your results of using the emission inventory for 2010 when your simulation time is 2014 to 2015?
So we saw a good comparison between the surface monitors, even using the 2010 simulation. But that's, definitely a limitation of the study.
What's the substituting energy source look called after the coal dice?
The what? Oh.
The substituting energy.
So we haven't looked at assuming any substituted energy source. So this is just zeroing out the emissions in that area.
So I have one question. So where did you calculate the cloud indirect effect?
We had an offline RRTMG model.
You can simulate the effect on clouds.
Yeah, exactly.
Albedo effect.
Mm-hmm. Cloud albedo, yeah.
Okay, thank you. Okay, thank you. Our next speaker is Matthew Jollins from Edinburgh, and he will talk about nitrate during the some winter campaign.
Thanks.
That's welcome.
Thanks. Good afternoon, everyone. I have to apologise. I'm another one of those people that have changed their talk and not updated the agenda. So sorry for those that were hoping to hear about PM2.5. I'm speaking about nitrate in Beijing instead, but I guess it's not a million miles away. So I work at the University of Edinburgh with Paul Palmer. I've not included the sort of various contributors we've had in terms of providing measurement data. There's quite a lot of them, specifically the Sun Group at IAP and the Lee Group at York, who provided aerosol measurement data and trace gas data, respectively. Okay, yes. So to begin with, just give an overview of the campaign itself. So APHH, or Air Pollution and Human Health, is a collaborative project between the UK and China to study air pollution sources and associated health impacts. It's quite a broad project involving around 30 institutions, over 200 participants and nearly 200 instruments. There's a lot of sort of different aspects to the project, including intensive measurement campaigns, flux observations, personal exposure monitoring, remote sensing and chemical transport modelling. The two measurement campaigns took place in November and December 2016 and May and June 2017, based at the IEP site in central Beijing, with additional measurements taken on the IEP meteorological tower. The sites are shown at the bottom between the 3rd and 4th ring roads in Beijing, and the location of various containers housing the instruments from different groups involved with the project. Just an overview of the GEOS Chem simulations we've included here. So use version 11.1 using the nested China domain with GSFP metadata, the semi-volatile POA aerosol chemistry mechanism, and make emissions for China. So this gives a bit of an overview of the model measurement comparison for a number of species. This is by no means comprehensive. There are a lot of additional measurements of VOCs and nitrogen compounds, photolysis rates, and a whole other range of measurements. I guess the best way to describe the overall picture here is a bit of a mixed bag, really, in terms of the comparison of GEOS Chem 2 measurements. There are the R-squared values sort of are pretty low across the board, really, for most comparisons. There are a number of sort of features which stand out, which are sort of seen in, I mentioned in the sort of previous questions that we've seen a lot of these types of studies. So the sort of particularly strong underestimate of sulfate in the model, and the overestimate of nitrate, which is what I'm going to focus on here. So this is just emphasizing the overestimation of nitrate in the model by around a factor of 4, which is sort of fairly consistent with the overestimation of nitrate emission ratios to CO in the model. So in quite a few talks and presentations this week, we've sort of heard about the sort of importance of additional sort of factors influencing this overprediction of nitrate, including chemistry and deposition processes. Well, I'm just going to give sort of an initial sort of overview of the potential for the influence of emission on the overestimation of nitrate. So to do this, I've performed a number of sensitivity runs of GEOS Chem involving reductions in ammonium nitrate precursor emissions. So the first of these was a reduction of NO by 50%, then a one with a reduction of ammonia by 50%, and finally a reduction of 25% of both NO and ammonia. As you can see, the reductions in NO and ammonia produce a very similar average reduction in nitrate concentrations throughout the period of focus, with a low reduction for the combined NO and ammonia simulation. This sort of seems to give an indication that the overall magnitude of the reduction seems to be having more of an influence in the sort of under typical Beijing atmospheric conditions than any sort of particular relationship to a specific precursor. However, this sort of produces a bit of a discrepancy in the reconciliation of the observed nitrate concentrations with the model. So despite the similar average reduction in nitrate concentrations from the reduced NO and reduced ammonia simulations, the reduced ammonia simulation produces a bigger decrease in the bias to the observations. And this seems to be influenced by a contrast between the sensitivity to emissions during clean and polluted periods, which I've assessed using by applying a CO threshold of 600 ppb to the data sets to define clean and polluted periods. This is slightly lower than typical thresholds for similar sort of assessments in Beijing. So previous studies have used a higher value of around 1,000 ppb, and also incorporated other metrics such as OH reactivity. However, using a higher threshold for the data here tended to introduce more clearly sort of photochemically aged material into the clean period. So the use of this threshold of 600 seemed to work better for this data. So this just sort of provides a validation of this, the polluting clean thresholds required. So this just shows the emission ratios of nitrate to CO with the color scale of NOx to NOI. You can see sort of clear change in the average values for the prescribed clean periods on the left of the plot and the polluted periods on the right. So applying this segregation to the sensitivity runs shows that for the reduced NO simulation, there's very little change in the sensitivity to reduced emissions between clean and polluted periods. However, there seems to be much greater sensitivity to ammonia under polluted conditions. And again, for the combined simulation, there's sort of a lower sensitivity overall to reduce emissions. So this is very much sort of something we work on doing. There's a lot more I need to develop further going forward with this. So I'll just leave that there for now. Thank you.
Have you looked at the overestimate in formaldehyde that you see compared to the observations?
Formaldehyde, sorry.
Yeah.
Yes, so formaldehyde seems to be fairly strongly overpredicted for the winter period. I've not really looked into it more than that at the moment. That's just sort of the initial finding. However, it varies for the summer campaign. So formaldehyde is particularly underestimated during the summer, so it seems to vary quite a lot sort of seasonally. But I've not done much more analysis on that yet.
What's a very your overestimate of nitrate, underestimate of the gas burn?
Yes, I think that's probably going to be quite a significant sort of contributor. I have looked briefly at the ratios of nitrate to ammonia, and there seems to be sort of very little variation for different emission scenarios. However, there does seem to be a slight increase in sulfate to ammonia under those sort of scenarios, but it doesn't seem really enough to sort of reconcile the differences with observed sulfate. But yeah, that is something that probably is going to contribute.
Kind of similar question, but did you also look at what the effect of the different emission scenarios was on the sum of nitric acid and nitrate? Was that more?
I haven't, no, I've not looked at nitric acid.
That might be a way to kind of ease out the effect of partitioning.
Yeah.
Okay.
Yep, thank you.
So our next speaker is Chen Gong from IAP, and he will talk about the effect of the transport of ozone and its precursors in central China on ozone pollution episodes in northern China. Let's welcome.
Okay, thank you. Good afternoon, everyone. I'm Chen Gong from IAP Chinese Academy of Science. I'm sorry about that. I changed a little for the title, but it's the same thing. And today I want to talk about the effect of the transport on ozone pollution episodes in North China. And as we know, in the past several years, the ozone concentration over China show an increasing trend. And here we focus on the ozone pollution episodes in North China. And here the episodes are defined as the observed MDA8 ozone concentrations averaged over North China larger than 80 pppa and persistence of over 5 days. And here we found that we found 9 episodes over May to July, which is the months with the highest ozone concentrations in North China. And we found that the maximum ozone concentrations during the episodes can reach about 130 pppa. This is a very huge concentration. And we also found that from 2014 to 2017, the ozone pollution episodes occur more and more frequently, and the ozone concentration during the episodes become higher, and the persistence of the episodes become longer. So there might be many possible reasons for this increasing trend. For example, there are more and more favorable weather conditions for this episode, and the ozone chemical production is become higher because of the changes in emissions. And recent studies show that the decrease on PM2.5 will lead to the increase of ozone concentrations. However, all of these possible reasons is the local factors that will influence the ozone concentrations. But there are few studies focused on the effect of ozone transports to the episodes. So here, we use the ground level ozone observations measured to realize the data geoscam packed ozone simulation and geoscam nested simulation in Asian region to investigate these questions. And here in the geoscam model, we use the MAC anthropogenic emission inventory over 2014 to 2017, which is provided by Tsinghua University. As for the method, here we use the composite analyze to study the normalized winds during the episodes, and we use the backward trajectories to study where the air comes from during the episodes in North China. And the tagged ozone simulation are simulated to quantify the contributions of ozone generated from other regions to the surface ozone in North China. And we run 2 sensitivity experiments to evaluate the effect of emission reductions on the episodes. As for the model evaluation, here the black dots shows the observed ozone concentrations over North China, and the green line and the yellow line shows the tagged ozone simulated ozone concentrations and the nested model simulated ozone concentrations respectively. And here we found that the model estimates ozone concentrations for the episodes. So here we use a reduced threshold in the model, and by using this threshold, 8 of 9 episodes can be captured by the model, which is highlighted by the red lines. So to begin with, here this figure shows the composites of the wind fields during the episodes at 850 hPa levels. And here we found that compared with the seasonal means, there is a strong southeast wind that will transport the ozone from central eastern China, which is enclosed by the red rectangle, to the North China. And also the backward trajectories in Beijing during the episodes shows that there are over 70% trajectories from central eastern China during the episodes. And this figure shows the cross sections, the latitude time cross sections for each episode. And the ozone concentrations and the wind fields are averaged over central eastern China or North China respectively at each latitude. And here we found that when the ozone concentrations become high in North China, it accompanies with the strong southeast winds that will transport the ozone from central eastern China to North China. So all of this evidence shows that there is a strong southeast winds that will transport the ozone from central eastern China to North China during the episodes. And then we use the tagged ozone simulation to quantify the contributions of ozone from other regions to the surface ozone in North China. And here 10 regions, including North China and central eastern China, are divided as this finger shows. And here we found that ozone generated locally in North China makes the largest contributions. But interestingly, compared with the seasonal means, we found that the ozone generated from central eastern China makes a significant increased contributions, while ozone from other regions change little. So in the tagged ozone simulation, we found that compared with the seasonal means, the ozone concentrations enhanced about by 10.5 ppb during the episodes, in which about 1/3, 3.7 ppb ozone are generated from central eastern China, and 2/3, 6.8 ppb ozone are generated from North China. So the tagged ozone can tell us that the ozone from central eastern China makes relatively important contributions to the formation of the episodes in North China, which is also very important to us to better understand the increasing trend of the ozone pollution episodes. Here, this figure shows observed ozone concentrations over eastern China from 2014 to 2017, and we can see that there is a significant increasing trend of the ozone concentrations. And the meridional wind that is the south border over North China also show an increasing trend during the episodes from Maratur as the data. So higher ozone concentrations, stronger southeast winds will lead to a stronger ozone transport during the episodes. And also in the tagged ozone simulation, we found that the ozone generated from central eastern China makes increased contributions to the ozone concentrations during the episodes in North China. So all of this evidence shows that there is the ozone transports become stronger, and it will lead to the increase of the ozone pollution episodes. And then finally, we run 2 sensitivity experiments with 50% NOx and 50% VOC reductions in central eastern China to quantify to evaluate the emission reductions in central eastern China to the ozone concentrations in North China. So here we found that the reductions in VOCs, which is the blue boxes shows in central eastern China, are more efficient to reduce the ozone concentrations in North China than the NOx, as the red box shows. And the emission reduction in central eastern China are helpful for reduce the peak contributions during the episodes in North China. And here is a summary. We found that ozone transport from Central Eastern China contribute about 1/3 to the ozone enhancement during the episodes compared with the seasonal means. And also, we found that the transport of ozone from Central Eastern China is increasing, which will lead to the increase in observed ozone pollution episodes in North China. And the sensitivity experiments shows that the reductions in VOCs in Central Eastern China are efficient to alleviate ozone pollution episodes in North China, especially for the peak ozone concentrations. Thank you for listening.
You see the increase in transport ozone from Central East China to North China. Do you see ozone decrease in Central East China?
The ozone trends in North China is increasing.
What about trend in Central East China?
Central East China is increasing. This finger, this is average over Central Eastern China.
So I guess the question is this trend, first of all, will continue? Is it due to meteorology from south to north, or is it due to increasing emissions in Central Eastern China?
So the question is why the ozone concentrations in Central Eastern China are increasing?
Yeah, is it meteorological or is it?
Well, this is a very, very interesting question. That's because we found that in the sensitivity simulation experiments, we found that the reductions in VOCs is reduce the ozone concentrations more. So, but actually, in recent years, the VOC emission in Central East China show an increasing trend. So the emission might contribute to, I don't know how much, yeah, but this is not the point of our study. Our point is to highlight the transport effect. Yeah.
In which season would you expect the largest effect on Central China? Because I would expect like different weather system and also different circulation.
Summer.
Yeah, summer.
Yeah. Because in summer the ozone pollution episodes occur more frequently.
Is seasonality large? Like.
Yeah, of course, because I don't know the transport variation in other seasons, but because in these studies we focus on the ozone pollution episodes. The episodes is most occur in summer. Yeah. I don't know the transport in other seasons.
So I have one question. So when you do your original attribution, did you just use the tag ozone or did you use the emission zero emission?
Tag ozone.
In this case, then, since you are using tag ozone, so I wonder, what's the source of the ozone in different tag region?
Source? We firstly run the GeoChem TropChem simulation, and we archive the chemical production and chemical loss rates of the ozone. And then we use account the chemical production rate to as a source for the tag simulation.
My question is that for example, for the ozone produced over Central China, what's the emission? Where are the emissions which drive the ozone?
Drives the ozone?
Which produce the ozone over Central China?
Well, in the tag simulation, the emission module is not loaded in the GeoChem module. Yeah, so I don't know the point. Yeah, maybe we can discuss later.
So, okay, thank you. So our next speaker is Xueying Liu from CU Hong Kong, and she will talk about the environmental and health impacts of diet change.
Yeah, thanks very much.
In China.
Yeah, in China.
That's welcome.
Yeah, and thanks very much. I'm Xueying Liu from Chinese University of Hong Kong. The work looks at the dietary pattern in China back in 1980s versus the present day and how it's affected PM2.5 and premature mortality in that region. The works in collaboration with Professor Amos Tai from CUHK, Youfan Chen, and Professor Lin Zhang from Peking U, and Professor Gavin Shaddick from Exeter. So dietary change is about the way that people eat, like the amount of food intake and balance between meat, crops, and vegetables. So we can see that both population rise and diet are both driving factors for more food production. And in the bottom left, I'm showing you the Chinese population, which has increased 1.3 times from 1980s to the present day. And the increase in population actually drives more food production. And at the same time, the increase in income and socio-economic status of the population have dramatically improved the dietary intake and nutritional status of the population. So the meat consumption per capita has increased 3 times from 1980s to the present day, while the cereal consumption per capita remains relatively steady over this period. So you can really see that back in 1980s, around those, people rely heavily on cereal to be staple food, but in the present day, people still rely on cereal, but the meat consumption is much more intensive. So we say that the diet in China shifts from a plant-based diet towards a meat-intensive diet. And the shift in diet actually shapes the food production in China as well. And the food production or agricultural production, however, accounts for 85% of ammonium emission in China. And ammonia emission in China actually can further causes PM2.5 in the air, nitrification in water bodies, and soil acidification. So from here, we can really see that agricultural production, on one hand, feeds more people, which is good, but on the other hand, can cause environmental problems. So again, both population rise and dietary change drive more food production. And here, I'm showing you the meat and cereal production of the total country. It has been increasing over decades. It's partly driven by the population rise because it's the total population of the country, total production of the country. But if you look closely, you can see that among the different uses of cereal crop denoted by different color here, the percentage that's used for direct human consumption is actually dropping over time, while that for animal feed has been increasing over time. So the shift in the diet towards a meat-intensive way actually increases animal facilities. So there's a lot of ammonia coming out of their manure. At the same time, the increase in crop production that's used for animal feed also increases the fertilizer usage. Both contribute to more serious ammonia emission and thus PM2.5. So that's what we know. But in terms of the health costs, the change in diet towards a meat-intensive way actually can cause direct health problems, including diabetes, obesity. At the same time, the dietary change leading to more ammonia emission and thus more PM pollution represents an indirect health cost that has never been quantified before. So in that study, what we are looking at is the impact, the indirect impact of dietary change to human health. So to understand this, we have these 5 scenarios. S4 keeps everything at present day level, so represents the 2010 production, while S0 represents 1980s production. So the differences between S4 minus S1 is the overall impact of increased food production in China. And then S1 minus S0 represents the impact that's from population rise alone if people keep their eating habits back in 1980s. The differences between S1 and S4 and S1 is the effect that from the dietary change alone with population rise are excluded. So the thing is, we have the increase in agricultural production and driven a lot of environmental problems. And we separate those into population rise and those into dietary change. And then we further, within the dietary change, separate them into the demand for crops that use directly for human consumption and that's used for another part is driven by our need for meat, which actually includes the production of meat as well as the crops that's used for feed. This actually represents the real demand for meat, instead of just looking at the meat production and ignoring the fact that some crops are actually used for feed the animals. So the data and method are listed here. We use the Chinese emission inventory from Professor Zhang, and then to drive geoscam to compute the PM2.5 of each scenario and apply the relative changes to the fine resolution 0.1 degree PM map from Professor Gaiman-Shadik. So that's the result. That's the ammonia emission back in 1980s, and that's the increase in ammonia due to dietary change alone, population rise alone, and both from dietary change and population. So you can see that dietary shifts actually accounts for around 70% of the total ammonia emission in China over decades, while population rise only accounts for 30%. And within the increase in ammonia emission from dietary change, the majority of the demand for meat actually causes 3 times larger emission than the demand for crops. And that's for PM2.5. You can see the increase in PM2.5 that is due to dietary change can go up to around 30 microgram per cubic meter in Eastern China, where overnutrition happens. So you can see that people in Eastern China may suffer both from obesity and diabetes directly due to dietary shifts, and from respiratory and cardiovascular diseases that is indirectly due to air quality. And that for premature mortality, dietary change alone can explain about 9% of the total premature death in 2010, and with the majority being driven by the demand for meat, while the demand for crops plays a minor role. So the message is that people eat more crops and more meat over decades, but the increase in meat actually drives more environmental and thus health problems than the increase from crops. Yeah, so I'll leave the message here that, yeah, thank you. Oh. Sorry, can you repeat the question? I just finding you. Oh, yeah. Actually, in this study, we look at the dietary change in China and its impact within China. But when we run the simulation, we actually can see the different the impacts a little bit further beyond China, but not too much. It's really the impact is really local. Yeah.
Did you include emissions from meat cooking PM?
Meat cooking?
Sometimes there can be significant matter that comes directly up.
No.
Go ahead.
Because diet change have more fertilizer manure that would increase soil oxidation. That could also.
Yeah, that's a good point, because soil NOx also increases the ozone pollution, so that's a good point to look at. Thank you.
Okay, so in order to control our water, so you also need to know how much food we need to have. So have you done like a rough calculation without the calculation?
How much food? I think the point is really between the balance between meat, crops, and vegetables. If we look at the calorie intake, maybe they are the same, or I mean, due to different diet choices, the calorie may be the same, but it's really what really matters is the nutritional status. So yeah, it's not just the amount.
Yeah, if you overcook my food, there's I think you don't need that much.
Yeah, actually, the foods, according to my memory, around half of that goes to the food waste. So maybe an effective way to elevate the problem is reduce food waste. It's just yeah. Thank you.
Okay, I think it's more okay. So our next speaker is Li from MIT, and she will talk about potential changes in the sensitivities of inorganic fine particle matter to precursor emissions in China. Welcome.
Thank you. I'm Ming Wei Li from MIT, and today I'll talk about our research on the potential changes in the sensitivity of PM2.5 to its precursors in China. So because the precursors of PM2.5, they are mostly come from the anthropogenic sources, previous studies have examined how the sensitivity of the PM2.5 to its precursors to help to identify the most effective control policies. And here I show an example of the sensitivity that is for China in 2006, and by comparing the changes in concentrations of PM2.5 by 10% reduction, by a 10% increase of the precursors of SO2, NOx, and ammonium emissions. And what we found is that in winter, the PM2.5 is most sensitive to ammonium emissions. However, in the summertime, the PM2.5 is more sensitive to SO2 and NOx emissions. And from yesterday's talk by Professor Qiang Jiang, we learned that Chinese anthropogenic emissions has decreased a lot for SO2 and NOx emissions, but the ammonium emissions have been stayed constant over the period. So in this project, we are interested in how the sensitivity change due to this large reductions in SO2 and NOx emissions. And to do so, the emissions of SO2 and NOx are predicted from an energy economic model, and we consider 3 emission control scenarios shown here. And we project the emissions from 2010 to 2030. And under the most stringent scenario, the EC scenario, the SO2 and emission and NOx emissions reduced by 60% and 30%. And this is similar to the trend that I just showed from the bottom-up emission inventory. And here in this research, I will present the sensitivity in 2010 and the sensitivity in 2030 under the EC3 scenarios. So to do so, we use the GeoSCAM simulation, and we first conduct this standard simulation, just changing the SO2 and NOx emissions, one for the emissions in 2010, and the other for the emissions in 2030. And then to get the sensitivities of the precursors, we further conduct the sensitivity simulations that we perturbate the emissions by 10%, either a 10% decrease. And then we repeat the sensitivity for all the 3 precursors and for 2 months, January and July, representing the summer and winter conditions. And also for the 2 emission scenarios, one is 2010 and the other is the EC3. And the sensitivity is defined as the difference in the concentrations between the 2 perturbation simulations versus the difference in the emissions. And here for the concentrations, we are using the population-weighted average concentrations as a proxy for its health impact. And then for the emissions, we are using the difference in the national total emissions with the unit of the gigamole per month. So here I'm showing the sensitivity first in January. And basically, it's a 3x3 matrix that shows the sensitivity of sulfate, nitrate, ammonium to the 3 precursors, SO2, NOx, and ammonium emissions. And here, if you look at the sensitivity in 2010, the inorganic PM2.5 is most sensitive to the ammonium emissions, and largely it's come from the nitrate. It comes from the nitrate. And also for the nitrate, it has a negative sensitivity to SO2 emissions. And if you compare the 2010 versus the EC3, which has the reduction in SO2 and NOx emissions, the sensitivity to ammonium emissions reduced by almost 30%. However, the sensitivity to NOx emissions, it increased by nearly a factor of 3. And to further look at what caused the changes in the sensitivities, we used this gas ratio, which is defined in the formula over here. And if this ratio is below, it's between 0 and 1, it means this is in the ammonium limited regime. That under this regime, nitrate and sulfate and nitrate will compete for the limited ammonium wall here. And because the regime is different by region and also by different time of the year, here I plotted the probability density of the daily gas ratio in January over East China. And the black line shows the condition in 2010, and then the blue line shows the condition for EC3. So, in 2010, you could see that most of the conditions, they are under the ammonium limited regime, which means that the sulfate will compete. So that explains where there is a negative sensitivity of nitrate to SO2 emissions in this figure. And also under this regime, nitrate is more sensitive to ammonium emissions rather than the NOx emissions. But when SO2 and NOx reduce, the percentage in the ammonium limited regime is decreased to 60%, and that leads to the lower sensitivity to ammonium emissions, but higher sensitivity to NOx emissions. And here I show the results for the June, for the month of June. And under this month, the PM2.5 is more sensitive to SO2 and NOx emissions, but overall the sensitivity is lower than that in January. And also the changes in the sensitivity has similar directions, which means that the sensitivity of ammonium reduced, but the sensitivity to SO2 and NOx is increased. However, the magnitude is much slower compared to what's in the January. And to conclude that is what we found is the PM2.5 is most sensitive to ammonium emissions, but when SO2 and NOx emissions continue to decrease over time, the sensitivity to ammonium will decrease, but the sensitivity to NOx emissions will increase. And then if further studies, if we compare the cost information of those emission control, they can help to design effective control policies. So yeah, that's what I'm happy to take any questions you have. Thank you.
So I was curious, we saw that we have a problem with nitrate in China. So if we were to fix it somehow, what do you think would happen to the sensitivity present day?
Yeah, so our results also suffer from the problem that we overestimate the nitrate. Actually, we did a sensitivity study where we fixed the nitrate. Well, there's like several possible ways to fix that, but that will change the absolute sensitivity over here, but for the relativity change over time, that wouldn't like change much. Yeah.
That's, no further questions. Let's welcome our last speaker of this session, Juliet Zhu from Sun Yat-sen University. And she will talk about how to re-estimate ammonia emissions based on current satellite observations of ammonia and the geochem simulation. Welcome.
So good afternoon, everyone. I'm Juliet. Now I'm at Sun Yat-sen University. By the time I submitted my title, I thought I can definitely finish this project at the time I present. But it seems like I had wrong estimation on the time I can spend on this project as being a new faculty. So I have to add my progress on this title. So let's begin the story. So during the last 2 days, we have been told many times that about the extreme emission control policy in China about the SO2 and the NOx. So the emission of SO2 and NOx has been declined significantly in recent years. However, for the ammonia emissions, there's no efficient emission control policy. So there's not much change on the ammonia emission. However, we know that there are increasing evidence showing that increasing evidence indicate the critical role of ammonia in forming haze in China. For example, the average contribution of the agricultural ammonia emissions in the North Central Plain was about 30% of the PM2.5 mass during a severe haze event in December 2015. And then most recently, there are three more papers that mention the ammonia emission control could be the next step of solution that can reduce the haze of China. And this will also bring out a question that whether reduce the ammonia emissions could add more acid rain. So despite the importance of ammonia emission control, there's another problem that we know that there is a big uncertainty in ammonia emission inventory. And this is mainly due to the difficulties in estimating the farming activities and the observations of expensive cost of ammonia. So the observations of ammonia data, institute data are precious. So I'm showing you now is the new network of ammonia surface observations, which is called AMON China. So this this plot shows the annual average of ammonia surface observations during 1 year from September 2015 to August 2016. And you can see that there are large spatial differences among the whole China region, start from 1 to 29 microgram per meters cube. And there are 53 sites in total, including the mountains, grassland, the desert, and urban. And all of the sites are selected to be far away, which means larger than 1 kilometer from a known source. So we will use this monthly average of this AMON data later. So we know that the AMON sites are limited in spatial and temporal. So the observations from the satellites bring us another opportunity to take a better look at the ammonia concentrations over the China. So here I'm showing you the very new ammonia products from the satellites, CRIS. So the CRIS is on the SOMI MPP satellite launched in fall 2011. And our pass time is 1:30 at the noon and at the midnight. And the detection limit is about 0.5 ppb, and the footprint is about 14 kilometers in diameter. And on the right hand, I show you an example of CRIS ammonia retrieval and with the corresponding averaging kernel. And we can see from the figure that the CRIS most sensitivity to ammonia between 950 and 700 millibars. And it has 4 times better noise compared to other satellite sensor, IGC. So, and it has TAS-like sensitivity and IGC-like spatial coverage. And the detail of the CRIS ammonia retrieval algorithm can be found in Karen and Mark's paper in 2015. So here, very exciting. This is the first bit of the CRIS ammonia observations over China. I'm showing you the surface observations. And there are a lot of interesting things going on here, but I'm not going to cover all of them. So, but I want to pick one of them, which is like, no surprise, there are hotspots around the Beijing area, like here. And then there are other hotspots, such as the desert in the China northern area and the eastern area. There's also a desert in the middle of a terrain basin. So about this desert, we have think a little bit about it, and maybe we think it might be because of the dust influence, and but our crease retrieval haven't got a method to get rid of that. So we will continue investigate this problem in the future. And later, let's compare our crease ammonia observations to the AMON site. So here I just pick out two sites. One is a background site, which is located in Taishan Mountain, and another is a polluted site, which is located in Tianjin, which is very close to Beijing, and it's an urban site. So yeah, I need to explain that. The black line represents the AMON site observations, and the blue box plot including crease retrieval, that location within the 25 kilometers radius around this site. And from this comparison, we can see that crease surface ammonia can generally capture the seasonal variations of AMON China observations, but the magnitudes are lower. This brings us to thinking about including more, maybe we need to include more vertical information when comparing to the in-situ surface observations. So let's move to the GeoScam simulations. Now I'm showing you, okay, I know it seems like I need to stop, but okay, let's see. So what we are going to do is, what we are doing now is we are doing the data simulation with crease ammonia observations and the GeoScam with the GeoScam and joint model. So we are defining a small domain instead of using the whole China region, and we will use the crease ammonia observations over 5 years and use the ammonia emission inventory developed by the Lin Zhang's group. And I will leave the summary here, but please use my last 1 minute to do a little advertisement as I'm building my group. So these are my research interests, and I'm hiring postdoc and associate research scientists. And then the graduate students also welcome. And please contact me if you are interested in any of this. And also my school, the Yangtze University, the School of Atmosphere Science, also hiring all levels of faculties. And it's a beautiful campus in a wonderful coastal city. So if you want to know more, come and see on May 19th at MIT for the introduction session. Okay, thank you. I will stop here.
I was surprised that the AMON data show so much ammonia in winter. Specifically, we were heard from Ming Wei that PM was ammonia limited in winter, but you have 5 or 10 ppb of ammonia in the gas phase. So how could ammonia be limiting PM 2.5?
Well, I have to say that our AMON observations is true. Yeah, and so.
You know, are they any good, those observations?
What?
Are they good, those observations? The AMON?
Oh, well. So I think our AMON only observed for a very certain time. So it's only observed the 2016 winter, and I think there have extreme events that time, and I think ammonia is extreme during that time.
Okay, so when you compare GC ammonia with your AMON ammonia, you see the light flow. Can you compare same time the sulfate nitrate? if they are off, you cannot use the data situation to adjust your ammonia emissions. Because the ammonia constraint be caused by errors.
Yeah, I understand. Yeah. Actually, that one is done by Yofan, and I think she haven't do that yet, but that's the next plan. And yeah, I haven't talk about this more. And if you want to see more details, you can go to see Yofan's poster, C29.
Okay. Okay. Thank you. Let's
Thank you.
all the poster presenters, please go from that side to here.
Agricultural waste burning is contributing to serious air quality and health issues in India. Current interventions have not been rolled out at scale that can make a difference. What we're trying to do is to design new interventions that can reduce the population exposure to PM2.5 from the burning with the application of geochem, a joint model, and a cost-benefit analysis of the socio-economic impact. Preliminary results show that changing the timing of the burning during the day can make a difference. Please come by for more discussion. Thank you.
Hello everyone, my name is Siddhant. I'm a student with Clyde Hill at MIT. As you all know, air quality in India is a very large public health issue, and studies have estimated it contributes to over 1 million premature deaths every year. Recent studies have also shown that a large fraction of this pollution is regional in nature and secondary in nature, making geochem a useful tool to study it. But the constraint has been that we haven't traditionally had observations to constrain the precursors and various aerosol species. So what we do here is use airborne AMS observations from the SWAMI campaign to try and do that in conjunction with satellite information. But come by C21. Thank you.
Hello everyone, this is Mrinmoy from University of British Columbia. So this is actually a proposed framework for assessing the air quality and health impacts in rural India. So we are actually doing a sampling in India with using low-cost sensors, and then we are actually aiming to develop and modify the emission inventory and updating the emission factors. Then we are going to do some simulations with geochem and updating the results and look out the different cases of scenarios. So do reach out to me if you have any questions and feedbacks about that. Thank you.
Hello, everyone. My name is Madhulika. I'm from Indian School of Business. So in order to estimate the health burden attributable to coal in India, we use the IIT Bombay Emissions Inventory, the 2013 IIT Bombay Emissions Inventory, and GEOS FP 2015 to run the GEOS Chem simulation model on Amazon Web Services on 2 case scenarios, one with thermal power plants and one without thermal power plants. Once the simulation is complete, we will be estimating the population exposure to emissions from coal and to calculate the health burden using the global burden of disease study. Please drop by my poster. Thank you.
My name is Xinhua Shen. I'm an assistant professor from University of Northern Iowa. We use geochem model to set the initial condition and boundary condition for our simulation. We work on chemical simulation to simulate the regional air quality in Southeast Texas area. Our poster ID is C24. If you stop by my poster, we can have more communications. Thank you.
Hello everyone, I'm Anqi Hu from New East. In this study, WRF and CSM was used to simulate meteorological data in the 2 cycles separated from 40 years under RCP6 from IPCC, take into account of the influence of climate change on the 3 meteorological parameters, we make an in-depth study on the influence of climate change on the stagnant weather in northern China. If you are interested in it, please don't miss it. Thank you.
Hello, I'm Gongda from Alice Group. Nice to see you all. And China implemented its first comprehensive emission control plan for autumn and winter in Beijing, Tianjin, Hebei region in 2017. And a similar policy has extended to the whole China. So we are trying to assess this air quality policy using surface observations, multiple satellites, and also geoscan. Please come and give comments. It's a privilege to have a scientist to talk about my study. Thanks.
Hello, everyone. I'm Lin Tang from UNIST. The North China Plain is a heavily polluted region with intensive agricultural production and heavy industry. The changes of PM 2.5 in North China Plain showed a previously downward trend after 2013, when China's government takes strict emission control policy. We evaluated the performance of different resolution models, geoscan models for simulated the severe heat days in North China Plain during 2013 to 2017. And we found that the severe heat days in North China Plain showed a previously downward trend. And two both model capture this trend well. So if you're interested in it, just come to my poster. Thank you.
Hello everyone, I'm Yu Fan Chen. As we all know, ammonia emissions in China exist in large uncertainties. So here we estimated ammonia emissions in China from agriculture during 2005 to 2016. With our improved ammonia emissions, we can better simulate the ammonia concentration when compared with the observation from among China. For more information, please come to poster number 29. Thanks.
Hello, everyone. I'm Minghao Chu. I'm a graduate student from MIT. Air quality benefits of renewable energy policy are seldomly evaluated empirically. Our work develops a statistical model to explore how hourly wind power influences power sector emissions and then project the impact on air quality and human health using geoscan. We argue that renewable policy is not effective for pollution reduction due to the nature of economic dispatch, and actual benefits could be achieved by considering the social cost of power production. Please check out poster at C30. Thank you.
Hi, I'm Xiaomeng from Columbia. We use satellite observations of nitrogen dioxide and formaldehyde as indicators of ozone precursors, NOx, and VOCs. And we use that ratio to diagnose the nonlinear chemistry of surface ozone. So on the long-term scale, we paste together observations from 4 satellites, from which we analyze the long-term trend of ozone chemistry in the past 2 decades across global cities. At short-term scale, we use the new tropomi data to look at the change of ozone precursors during the wildfires. So please feel free to come by my poster if you're interested in the ozone chemistry from the view of space. Thank you very much.
Hi, I'm Michael Cheeseman. I work with Dr. Jeffrey Pierce at Colorado State University. And as many of you know, we derive global estimates of surface PM 2.5 from satellites using a combination of aerosol optical depth measurements and a modeled relationships between surface PM 2.5 and aerosol optical depth. So our team developed lower cost sensors of both surface PM 2.5 and AOD, and we deploy networks of these sensors by training citizen scientists around northern Colorado. And we find a lot of sub-grid scale variability. Please talk to me at C32. Thank you.
Hi everyone, I'm Yanda Zhang from Suni Avenue. As the last one, maybe I can take some flexible time. So as we all know, mineral dust is one of the most important cloud as nucleating particles. So in order to study the dust number concentration over the northeastern United States, we use the geoscan MEPM model to study the seasonal variation and the long-term trend of dust. In the past 18 years, we can see there is quite a strong decreasing trend. And also we looked into different regions and different seasons and found out quite a high correlation between dust and precipitation. I know this seems not very chemistry, but if you are interested in dust or in precipitation, I will be very appreciated to have you at my postdoc, which is C33. Okay, thank you very much.
Okay, thank you to all the speakers, and thank you to Jin Wright for giving everybody enough time. So now we're gonna break, and we're gonna